Finding a new life-saving drug, it used to be like searching for a needle in a haystack. But what if, instead of searching for that needle, you could just design the perfect one from scratch? Well, today, we're going to dive into the world of digital drug design, where computers are absolutely revolutionizing how we create new medicines.
So let's start with the big question. How do you even discover a new medicine? For decades, the answer was basically a whole lot of trial and error. It was a process that could take years, cost billions, and honestly, it often just came down to getting a lucky break in the lab.
Okay, think about it like this. Imagine a disease is caused by some kind of broken biological lock inside your body. A drug is the very specific key that can fit into that lock and, hopefully, fix the problem. For years, the only way you could find that key was to just test millions of random ones, hoping one would click. It was the ultimate needle in a haystack problem. And the sheer scale of this challenge, it's just staggering. Thanks to modern biology, we now have these incredibly detailed 3D maps of over 100,000 different proteins in our bodies. That's more than 100,000 potential locks we could target to fight all kinds of diseases. The old method of just randomly testing keys, well, it's completely overwhelmed.
But this is where computers completely change the game. We're stepping into an era of digital drug design, and it's allowing us to be smarter, way faster, and so much more precise in our search for cures.
So this new approach, it kicks off with a really revolutionary idea. Instead of randomly searching for a key, what if we just study the lock first? By using computers to understand the exact 3D shape of a target protein, we can digitally design the perfect key right from the start.
Now, there are two main digital strategies here. The first is called ligand-based design, which is kind of like finding a key that works okay and then trying to copy it to make a better version. But the real game changer, the one we're focusing on, is structure-based design. That's where you start with a 3D model of the lock itself, and you design a brand new, perfect key to fit.
And look, this isn't just some pie-in-the-sky theory. As the research shows, this mashup of computer work and traditional lab work is incredibly powerful. The computers can sift through millions of possibilities to find the most promising candidates, which means the scientists in the lab can focus their precious time and resources only on the ones most likely to actually work. It's basically the perfect partnership.
Okay, so how does a computer actually do this? How does it test a digital key in a digital lock? Well, the process is called molecular docking, and it is just as cool as it sounds.
Right. The core technique here is called molecular docking. It's essentially a super sophisticated simulation. The computer takes a digital model of the drug molecule, that's our key, and it tries to fit it into the active site of the target protein, our lock, in every single way imaginable to find the most stable, most effective fit.
And this whole process, it really boils down to two main phases. First up is the search, where an algorithm explores all the countless ways the key could possibly fit into the lock. Then comes the score, where a different algorithm rates every single one of those fits to find the absolute best one.
So let's dig into that first phase, the search. It's exactly what it sounds like. The algorithm is incredibly thorough, digitally wiggling, twisting, and turning that potential drug molecule in millions of different ways to map out every possible interaction it could have with that protein.
And there are a couple of different ways the algorithms can actually run this search. A systematic search is very methodical, like trying every single number on a combination lock one by one. It's thorough, but it might get stuck on a good enough fit. A stochastic search is more like randomly spinning the dials. It's less predictable, sure, but it's got a much better shot at hitting the absolute jackpot, even though it takes a ton more computer power. All right, so once the search has found all these possible ways the key could fit, we gotta know which one is the best. That's the job of the score phase. A scoring function acts like a judge, calculating something called the binding energy for each fit. And it's simple: the lower the energy, the more stable the bond, and the better the key fits the lock. It's like a puzzle piece snapping perfectly into place. And there are actually a few different ways to keep score, so to speak. Some methods use pure classical physics, calculating all the forces between every atom. Others use a simpler, faster method, grading the fit based on key things like hydrogen bonds. And some of the smartest systems are knowledge-based. They've basically studied thousands of successful drug-protein pairs to learn what a perfect fit looks like.
Okay, this all sounds amazing in theory, right? But the real question is, does it actually work? Are we going from pixels on a screen to actual pills that help people? The answer is a huge yes. Well, let's take a look at the fight against tuberculosis. Researchers used a multi-stage virtual screening process, and they successfully found brand new molecules that could block a critical enzyme called NHA. This enzyme is absolutely essential for the bacteria to build its cell wall. This is a brilliant way to find new weapons to fight these ancient diseases.
Or how about cancer? In one study, they did a virtual screen of a whopping 345,000 compounds to find new molecules that could shut down the proteasome, a key target in cancer cells. This process didn't just find active compounds. It led to a lead drug with excellent metabolic stability, which is absolutely crucial for a drug to work properly in the human body.
And here's a great one from diabetes research, where scientists ran into a really tricky problem. The target lock they were going after was kind of wobbly and flexible. So by using even smarter simulations that could account for that wobble, they were able to discover 15 new and powerful inhibitors, opening up a whole new way to treat diabetes complications.
So, where do we go from here? What's next for this incredible technology? Because while it's already so powerful, it's not perfect yet. Scientists are constantly pushing the boundaries to solve the next big challenges.
Yeah, to really take this to the next level, scientists are working on some pretty tough challenges. Things like predicting the exact strength of that bond, getting even better at dealing with those wobbly locks, and accurately modeling the super complex, watery environment that is, a human cell.
But look, even with those hurdles, the takeaway here is crystal clear. This digital approach is a massive leap forward. Virtual screening is slashing the time it takes to find new drugs from years down to months, saving unbelievable amounts of time and money, and paving the way for the medicines of tomorrow. And that leaves us with a final, really inspiring thought. With the power to digitally design a key for almost any biological lock out there, the question is no longer if we can find a cure for disease, it's what disease do we design a cure for next?